Hello, my name is Jared Skeens and welcome to the Zoom room. Today we'd like to cover the Statistics 1 specimen paper for 2020. So remember the Cambridge A-level for, actually it's called the Probability and Statistics 1. I just shorten it to Statistics 1. Sometimes it's referred to as the S1, but the Probability and Statistics 1 exam. And remember that 2020 enters into a new syllabus cycle. So by using the specimen paper, it gives us a little bit of a glimpse as, how they might treat new content, which in the statistics book, there's really only one topic that's new, and that's the geometric distribution. So let's go ahead and look at the specimen paper. Again, for the sake of time, we're not going to do all the questions on the board. Rather, I've already done them on the paper and scanned it so we can follow along together and go through an entire exam paper so that you can see all the different question types put together at one time. Now, so here, notice it says it's called paper 5. It's probability and statistics 1. In the past syllabus cycle, this was paper 6, but remember the mechanics 2 was removed. So now you have paper 1 is pure maths 1. Pure Maths 2 is the first half of the second book. Pure Maths 3 is the full second book, or the second half of the second book. And then you have mechanics, and now it's just paper 4 mechanics, not mechanics 1 or 2. And so that moves up the statistics, the probability and statistics 1 to paper 5. And then if you were to do probability and statistics 2, that would be paper 6. So notice this is now paper 5. In the past, it was paper 6. So you're going to have to watch those numbers in the future. You're used to seeing like 61, 62, 63. Now it's going to be paper 5, so 51, 52, 53. Also notice this is again for 2020. That's our new syllabus cycle. See the list of formula here. The new formula sheet is MF19. So you should have a separate formula for that. If you're looking here, it says there at the top, probability and statistics. And so you have, this is your paper for that. Although this does also include for probability and statistics 2 as well. So you don't need all of these formulas for this exam, but you should have that handy with you in case you need to look up some of those formulas. When you get into test time and you're a little nervous, your memory isn't quite as clear as what it is, before the test. So make sure you have your formula sheet, this MF19, there with you. And then notice it is still 1 hour and 15 minutes, the same as what it was in the previous syllabus cycle. And so again, my rule of thumb is 7 to 5, 7 to 5 ratio. You have approximately 7 minutes to do 5 points worth of Cambridge question. So these are some things to notice as we move forward into this new syllabus year. And again, the total mark for the paper is 50. So there's not as much of a change for the statistics. There was a little bit more of a change for the pure maths 1. So here the time and the point value still the same, just a different formula sheet that you're working with, and the paper number is now different. Okay, let's get started. So as we move into the first question, please follow my cursor as it will kind of coordinate with what I'm saying. For number 1 here, the following back-to-back stem and leaf diagram shows the annual salaries of a group of 39 females and 39 males. So notice here's 39 females. If you add up these numbers on the side, it should be 39. And if you add up these numbers over here, it should also be 39. Here's the labels at the top. Now, this is with data representation. In this question, they've given us the diagram. Sometimes you have to make the stem and leaf plot yourself. Here they've provided it for us. Also notice the key. The key is 2, 20, and 3. Comes from right here. Here's the 2, here's the 20, and here's the 3. Now when I make my own key, I prefer to use the ones right next to the stem. So I would have used like 0, 20, and 3, or 0, 21, and 0, something like that. But they use the 2, 20, and 3. This is important for interpreting the value of these numbers. So notice it's 20,200. That's going this way to the left. 20,200 for females and 20,300 going to the right for the males, meaning the stem is in thousands and the leaf is in hundreds. So the stem again is 20,000, and then the 2 and also the 3, those leaves are hundreds, 200 and 300. So it says, find the median and the quartiles of the female salaries. So again, read carefully the instructions. Here's our female side, and median is middle. Quartiles would be Q1 and Q3. So we want to take our 39, cut it in half, and then take each of those halves and cut them in half again. So if there's 39, that means there's an exact middle. So if we take the nearest even number, 38, divide by 2, that's 19. So we have 19 halves with an exact middle, which would be the 20th value. So here we see, here's 4 and 9, that's 13. So this one, again, remember you're reading from the stem outward. So this one here, this 0 here would be 14, 15, 16, 17, 18, 19. So the 20th value would be the 7. So the median is 22,700. That's the middle, the median. So that means we have 19 values in front of it and 19 values after it. So now we want to find Q1 and Q3. So 19 is also an odd number, so it also has an exact middle. So the nearest even number is 18, divided by 2 is 9. So that means the 10th value is the quartile 1, or if we count 10 also from the median, that will be quartile 3. So starting from the front, here's already 4. So 5, 6, 7, 8, 9, 10 is this 7 right here. So 21,700 is our Q1, first quartile. If we go 10 after the median, or even if we go 10 back, might be faster to go that way. Here's already 2 and 4, that's 6. And remember, if you're going backwards, you're going from the outside in. So here's already 6, 7, 8, 9, 10. So either you count 10 from the median or you count 10 back from the end, and you get to this 0 right here. So this would be 24,000, and then of course no hundreds, so it's all zeros. So 24,000 is the Q3. Now it says for part B, they give you the median and Q1 and Q3. Lower quartile is same as Q1. Upper quartile is same thing as Q3. They give us this for the male side. If you went through and figured it out, those would be the median and the quartiles for the male side. They provide it for you. And they want you to draw a box and whisker plot for both of those on one diagram to represent the data. So again, make sure you put a title, so salary. We also designate the female versus male box and whisker plot. And probably one of the most important features of box and whisker is creating the scale. Now notice this is only 3 points. So you've got like maybe 5 minutes to do all of this. You've already got the information, but you need to draw it. Don't spend too much time making it perfect. You don't have time, but you do want a good scale. So notice I just start at 20,000, which is the lowest value. 20,000 is right here, 20, 0. That's the minimum value. The maximum, I underlined it. So 20,000, and the maximum value is this one over here, 26,600. So minimum 20,000, maximum 26,600. Those are the furthest apart values. So I go from 20,000 to 26,600. There's not a nice really divisor for that. So I just used a scale of 10. So if you count here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that means the difference is 6,600 divided by 10 means that 1 centimeter is $660 worth. So you're going to have to kind of, estimate fairly accurately these spots. So here's the 20,000, that was the lowest value. Over here, the highest value is 26,000. You just put in your numbers. So 20,000, then you have to figure out where 21,700 is according to this. So here's 21,700. Here's the median, which is 22,700. Here's the 24,000 right here. And then the maximum value is 26,500, just a little short of the end here. Then the male values they put up here. So the minimum, you have to look, 20,300. So it's over just a little bit. It's not at the end. So 20,300. And then you have first quartiles, 22,600. Notice it is 22,600 is almost the same as the median of the previous one. Okay, almost the same. Then you have the median for this one's 24,000, third quartiles 25,300, and then of course the maximum was 26,600. So you need to make sure this, remember, is your 5-number summary. If you remember that, the 5-number summary, the minimum, Q1, median, Q3, and maximum. You need all those 5 numbers for both the male and female box and whisker plot. Once you get your 5 dots established, then you just draw the whiskers as a straight line. The box doesn't really matter how tall it is, as long as it's clearly a box, and your points are proportional to your scale. So again, you only got 5 minutes, so you want to make sure that you have your method, your system down on how to do that. So there's your box and whisker plot. Now we move into basically the second topic that we covered in statistics, which was mean, variance, and standard deviation. Again, these are using the alternate formula, which is not in your formula sheet. So you needed to memorize that alternate formula. If you don't remember, go back to that video part 2 in that data representation unit and go to that part 2 video to look at the alternate formula. How do we know it's alternate? Because we are reducing all the values by 50. So instead of what I called the big number set, or your original number set, is being each one reduced by 50, so that gives you a small number set. So that's what these values are from. This one is from the mean, and this one is from your variance formula. So find the variance of the speeds, and then find this sum of x squared, which would come from the original set, not the reduced set. Remember also that variance is spread, and the spread is the same for both the big number set and the small number set. In other words, the big number set is the original values. The small number set is after you've reduced each value. So the spread is still the same. So we can use that to our advantage. So how do we find variance? Well, because they give us the small number set information, we need to find the small mean. And the small mean is this sum of the small number values divided by how many values there are. So the 81.4, that's the sum, divided by how many, that gives you the small mean. This is the mean before you add back the 50. If you add back the 50, that is the mean for the original data set or the big data set. Okay, so this is the mean for the small data set. So to find variance, you use this sum up here of the squares, again, as of the small value set, 671 divided by the total number, which is 22, and then minus the mean squared. And this mean has to be the small mean squared because we're using the small data set. And that gives us 16.81. So there's our first answer, 16.81. Now, since we want to find information of the original set or the big value set, we need to now find the big mean, or in other words, the mean of the actual data set. So we add back the 50 and we get 53.7. So remember, mean is a location. So your small number set is separated by 50 points from the big number set. That means your mean, which is a location, changes by 50, but variance, the spread, stays the same regardless of which set you're working with. So the big mean is 53.7. Notice we keep the same variance because the spread does not change. We're looking for the sum of our big number set divided by 22 minus now our big mean squared. This again is variance because it doesn't change. And we can solve for the sum of x squared. So we have to add the 53.7 squared first. That gives us 2,900.5. Then multiplied by the 22. So your sum of x squared equals 63,811. Moving on to question 3. Now we get into some permutations, combinations question type. So a book club sends 6 paperback and 2 hardback books to Mrs. Hunt. Out of those, she chooses 4 at random to take with her on holiday. The random variable x represents the paperback books she chooses. Show that the probability that she chooses exactly 2 paperback books is 13 over 14. So out of these 6, she's going to choose exactly 2. Now remember, this is a selection to a group to take with you. It doesn't matter the order in which she has the books, just that she selects them to take with her on holiday. So this is combinations, not permutations. So from the 6, she's going to choose 2. Well, if she's choosing a total of 4, that means she has to choose 2 more, and there's only 2 hardback books. So that means obviously she has to choose both of those. And this is asking probability, which means in the denominator, we need to do our total possibilities. And so there's 8 books, and she's choosing 4. So on the top, 2C2 is just 1, and 6C2 is our 15. And then there's a total of 70 different possible ways of choosing 4 books. 15 of those involve 2 paperbacks, and that reduces to 3/14. Now this here, even though I put the work above the question, it goes with this question here because the paper changes and I didn't want to write on the next page. So I just put it up here so I could see what I'm doing. Draw up the probability distribution table for x. So remember, on top is your little x, that's the possible values that it can take. On the bottom is our probability. What is the probability that our random variable, that's the capital X, equals the little x, which is the particular values it can take? We already calculated the probability for 2 paperbacks. It was the 3/14 from up here. That's our 2 paperbacks. So 3/14 we already did. Now for 3 paperbacks, by the way, there's 6 paperbacks and 2 hardbacks. So this is the number of paperback books. So at most, because she's only selecting 4 books total, then out of those 6 paperbacks, at most, she can only select 4 because she's only choosing 4 books. And minimum, she can only choose 2 because there's only 2 hardbacks. So if there's only 2 hardbacks, the other 2 have to be paperback. So 2, 3, and 4 are the possible values that the paperbacks can take. So you might want to take a little time to think that through, your minimum to maximum. And again, look at how many she's choosing, how many of each type there are, so that you get the correct numbers here, 2, 3, and 4. Again, we've already calculated the 2. So up here is our calculation for 3. 6 paperbacks choose 3. That means of the 2 hardback, we're only choosing 1. This equals 4. Our 8 choose 4, again, was the 70. So I just wrote the reduced value here. I didn't write the full simplification. So this simplified comes down to 4/7. Notice when I put it in here, I did put 4/7, but underneath I put 8/14. I like to keep the same denominator. It's easier to double check here at the end. This one is for the 4. So 6 choose 4 for the paperbacks. Again, that would mean no hardbacks. 2 choose 0. And then, of course, our probability 8 choose 4 on the bottom. This reduces to 3/14. And so here we have 3/14. It is very common to see the symmetry in binomial distribution. So 3/14, 8/14, back to 3/14. We see a symmetry. I double check to make sure that I'm doing it right by adding up all the probability. So 8, 9, 10, 11, 12, 13, 14. 14 over 14 does add up to 1. So that's kind of your double check to make sure you haven't forgotten a possible value or that you haven't miscalculated one of your probabilities. So that's a good sign that you're doing it right. And that was our probability distribution table, which we covered in the 2nd unit. This one up here, this kind of probability, was actually in our last unit, permutations and combinations unit. So notice how they mix the question types. Here now we're given or asked to find our E of X. Remember, or it gives us the E of X. Remember, that's mean. Your expected mean is 3. And this is the formula. Well, they give you the answer, but this is what you calculate from a probability distribution table. And they want you to find var X. So remember, from a probability distribution table, you square the X values and you multiply it by each of their probabilities. You add them up and you subtract the mean squared. So here's 2 squared times 3/14 plus 3 squared times 4/7, that was the reduced value, plus 4 squared times 3/14. You add all of those up and subtract the mean, which is this right here, the E of X squared, so 3 squared. And you go through and simplify it all out, and at the end you get 3/7 or 0.429 to your 3 decimal places there, or your 3 significant figures rather. So 3/7 or 0.429 is your answer for that. That's just following your formulas. These, by the way, are in your formula sheet. You can look it up and see the formulas there. Now we move on to a normal distribution. Notice how I underline and circle things as I go. A petrol station, petrol gas station, benzene station, whatever you're used to calling it, petrol station finds that its daily sales in liters are normally distributed with a mean of 4,520 and a standard deviation of 560. Find how many days, so we're still looking at days, of 365. Okay, so how many of these 365 are expected to be above, exceed 3,900? Okay, so we're doing normal distribution here. So the first thing we do is we write our notation. So our random variable x is distributed normally. And here are the parameters. The mean, 4,520. Now remember, this parameter is variance. They gave us standard deviation, so we need to put 560 squared. Variance is the square of standard deviation. And we also need to write our probability statement. So our probability is that the random variable exceeds, so it's greater than 3,900, and we need to find the probability so that we can find how many days. So we follow our flow chart that we learned for normal distribution, and we need to make a couple of observations. First, we plug the 3,900 into our x value, minus the mean, divided by standard deviation, not variance, standard deviation, so just the 560. So the x value, that is from here, our particular value that we're finding the probability for, minus the mean, divide by standard deviation equals a negative 1.107. Now we need to make a couple of observations. First, your phi z chart is not for greater than. Your phi z chart shades less than. Your phi z chart, by the way, is also in your formula sheet. They provide a phi z chart in your formula sheet. So you look at that phi z chart, and if you notice the graph at the top, it's shaded to the left, the less than. This is a greater than. So that means we need to do a 1 minus our probability at the end. Also, our phi z chart cannot do negative z's. It can only do positive z's. That z column on the left is positive values. This one is negative. So we need to switch our z to positive, and then we need to remember to do a 1 minus p. Now, because we're doing 1 minus p twice, well, it just cancels itself out. So if you can remember that, you really don't have to do anything to your answer, because 1 minus something gives you the other part, and then when you 1 minus it again, it gives you the part you just had. So those two cancel themselves out. So our phi z for the positive z, you can look up the 1.1 in the first column, the 0 in the top, and then the 7 on the right column. So with the 1.1 lined up with the 0, you get 0.8643 in the middle. That's your probability number. And then if you look at the 7 on the far right column, you have to add. This is addition. I didn't put the plus sign, but this is adding another 14 to the end of the number. So our probability is 0.8657. So about 86.5% is your probability. And we want to find how many of these 365 days would we expect to exceed the 3,900 liters of gas. And so we multiply our probability times the 365, and that gives us, rounding to the nearest day, approximately 316 days that we would expect the sales to be over 3,900 liters. So that's our probability distribution. Now, guess what? They give us another one. The daily sales at a different gas station or petrol station. Again, the capital variable X is representing the liters. It's normally distributed. This time, they do not give us the mean. The mean is M. It's this unknown variable. They do give us the standard deviation, which is 560, and they give us this equation, the probability of our random variable being greater than 8,000 liters is equal to only 0.122 or 12.2%. So they give us the answer to the probability, but they don't give us the mean. And if you remember in our mind map, our map of how to get through it, the mean is right here. So that's where we have to find our answer right here. First, write your notation. Our random variable is distributed normally, and here's our parameters, the mean and our standard deviation, so we want to write it as variance, 560 squared. And then our probability distribution, or sorry, our probability statement, probability of our random variable being greater than 8,000 is equal to 0.122. Again, we have a greater than sign, and in order to use our phi z chart, we need less than. In this case, it is to our benefit because they've already given us probability, so we can change the sign and we can do 1 minus the probability they have given us. The reason why this is to our advantage is because not only can the phi z chart not do greater than, it also does not have values under 0.5000. That's the starting point. It starts at the 50% and goes up. So we can't actually read 0.122 in the phi z chart. So by switching the greater than to less than, and then adjusting that by doing 1 minus the probability, we get both the less than, which is what we need, and we get a value that we can actually find in the chart, 0.878. Now remember, this is probability, not your z number. So this is not the left-hand column in the upper row. This is the numbers inside your chart, the probability numbers. So you're searching for 0.878 or the number that is as close to it as you can get. And I think actually for this, you look at phi z, and when you look at 0.878, you're going to get a 1.1 for the first column, corresponding with 6. Now that's not going to give you 0.878, but it's going to give you a number close to it. I probably should have wrote it on here. I didn't. You're going to have to look at how much you're going to have to add to that to get 0.878. And if you look in the 5 column in the far right, it will tell you how many points that you should add to it. So when you take the 1.1 cross-referenced with 6 at the top, it gives you one number. And then when you add to it what the far right column says for the value of 5, whatever that number is, and you add them together, it should be 0.878. So I probably should have wrote that a little bit more clearly on here. I was just solving this myself, so I kind of skipped the step. But 0.878, you should end up with the z value of 1.165. Again, we do not have to do the 1 minus because we already did it up here. We already did the 1 minus up here, and it flipped the inequality in the direction that we want. So 8,000 is our x, 560 is the standard deviation. We're solving for m. So again, I skipped a couple of steps here. If you multiply by 560, add m to the other side and subtract this value from the 8,000, you should be able to do this. This is just simple algebra here. Your m, or your median, your mean, your average number of liters that this gas station sells is 7,347.6 liters of gasoline is the average for this gas station. Okay, so that was just another variation of the normal distribution question, just put the variable in a different spot. Now, says find the probability that daily sales exceed 8,000 liters on fewer than 2 of 6 randomly chosen days. Now, mentally, you really have to be sharp because Cambridge, on every A, B, C, they're kind of changing things. The first two were normal distribution, and they just changed the variable that they're solving for. This one, all of a sudden, you're not dealing with liters of gas, which is a continuous concept. You're now dealing with number of days. That's a discrete concept. So this is actually binomial. So pay close attention to what you're actually looking at. Come back here. Notice this is about X liters. Okay, that's continuous. The amount of liters is continuous data. That's why it's normal. This one is about daily sales. Days are discrete. 1 day, 2 day, 3 day. You don't go by parts of a day when you're talking about daily sales. So fewer than 2 of 6. So again, you need to recognize this is discrete and there are a fixed number of trials. So it means we're binomial, not geometric, right? So 6 is our n, so we write our notation, our random variable, which is now daily sales, not liters, distributed binomially because this is discrete data, has the parameters of 6, that's our fixed number of trials, and the 0.122. Now, where did we get that from? Notice it says it exceeds 8,000 liters. Oh, that was back here. The probability that it exceeds 8,000 liters is 0.122. So you had to look back to find this probability. It's 0.122. Notice this is the same petrol station as back here. See, this up here is the main heading. So this applies to B and also to C. So this main heading of information applies to both of it. So this right here is where you get your probability of success, 0.122. That's here. That means your probability of failure is the 0.878. And if you want fewer than 2, then that means your probability of X is less than 2, not equal to 2. So we need to change this into what exactly that means. That means the probability that X is equal to either 0 days or 1 day. 0 and 1. Don't forget 0 is a possibility. 0 and 1 are less than 2, and you can have 0 days. So we plug that into our binomial formula, which is in your formula sheet. And so you have 6 days, choose 0. So we're doing the 0 first. 6 days, choose 0 with 0 successes and 6 failures, plus 6 choose 1, 6 days choosing 1 day with 1 success, 5 failures. You calculate that on your calculator using your NCR key and your exponent keys. You multiply all this out, you get this number, multiply this out, you get that number, add them together, you get this number, and to 3 significant figures, you have 0.840 as your answer. Moving on, we go back to, or this case, we're using an approximation. It says a fair 6-sided die, fair means equal chance for each value, with faces marked 1 through 6 is thrown 90 times. Okay, that's your number of trials. Use an approximation to find that a 3, when you roll the die, is obtained fewer than 18 times. Now, your number of 3s is fixed. If you roll the die, you either get a 3 or you don't. You're not going to get half a 3. So this is discrete data. How many 3s you get are going to have positive integer values. okay, with no in between. So this is discrete with a fixed number of trials. So this again is binomial distribution, but 18 times would be from 0 to 18. That would be 19 different calculations. Or if you went the other way, well, you're looking at like 72 different calculations going the other way. That's too many calculations. That's why we want to use an approximation. So first we have to start with our binomial notation. So our random variable x is distributed binomially with fixed number of trials, 90, and the probability of getting a 3, well, that's just 1 out of 6. So you just have simple probability there because it's a fair die. So 1 out of 6 values, that's your probability of success. I didn't write it down, but that means your probability of failure is 5, 6. Your probability statement is the probability that the number of 3s, which is your random variable, is fewer than, less than 18. That's your probability statement. We want to find the probability. We're looking for the answer. Well, remember this is binomial. And discrete data, the inequality matters. So if we are less than 18, the next discrete number below that is 17. So actually, this is the probability that x is less than or equal to 17, okay? Then we need to convert this over to normal because we're going to use normal to approximate the binomial so that we're not doing, I guess it's 18 different calculations from 0 to 17. Okay, so we're just going to do one calculation with the normal method. So we have to convert our information. So remember now our random variable is distributed normally. And to get the mean, you do n times p. So 90 times 1/6 is your 15. This is np. And then your variance is npq. So 90 times 1/6 times q, which is your failure, which is 5, 6. 90 times 1/6 times 5, 6 is 12.5. That's your variance. And we need to convert from our discrete data. We have to use our continuity correction for our continuous data, just like you did with histograms and cumulative frequency with the grouped information. You did that 0.5 on both sides. Since we are going less than, and we need to include this 17, the 17, we need to include it. That means we have, and we're going less than, that means we need to take the right-hand value. In other words, we need to add 0.5, okay? So we need to add 0.5 to it. So here's 17, look at the cursor, here's 17. We want to go less than. Well, if we go to 16.5 and go less, we're missing the 17. So we need to do the 0.5 on the right, which is 17.5. That way, when we go less than, we are including the 17. Okay, so 17.5 is with the continuity correction. Plug that into the x. So our z value equals 17.5 minus the mean, 15, divided by, now remember this is standard deviation, which is the square root of variance. There's no square written here. So that means we have to square root that number. The square root of the variance is standard deviation. When you calculate this, you get a 0.707. That's our z number. So we looked that up in the phi z chart. When you look up 0.7 cross-referenced with the 0 at the top, so the 0.7 on the left column with the 0 on the top row gives you 0.7580. And then when you look at the 7 on the right column, it says to add 21. Again, I didn't put the plus sign here. You're adding 21 to the end, and that gives you 0.7601. So you can put 0.7601 as your answer. And because this is exact, with these kind of things, I would put all 4 numbers. I wouldn't do 3 significant figures, because this is exact values. It's not a rounded value. So don't do 3 significant figures for these probabilities from your z-chart. These are exact. So put all 4 digits, 0.7601. Then moving on, it asks for an approximation. If you remember from the video where we did normal to approximate binomial, the justification, you have to do n times p and n times q. That is your number of trials times the probability of success, and that value needs to be greater than 5. And then your number of trials times the probability of failure, so 90 times 5, 6. That number has to also be greater than 5. Do not just put 15 and 75. You need to show the interpretation. So 15 is greater than 5 and 75 is greater than 5. That then is your justification. Okay, on another occasion, the same die is thrown repeatedly until a 3 is obtained. This is your new content. I didn't write new here, I probably should have, but this is your new content for the 2020 syllabus. This is the geometric. So notice obtaining a 3 is discrete. You either have a 3 or you don't, and the number of 3s that you have follow integer values. You don't have half a 3. So this is discrete, but you do not have a fixed number of trials. You keep throwing until you get the 3. So this is your geometric distribution, and it wants you to find the probability that you obtain a 3 requires fewer than 7 throws. That means 6 or less. There's different ways you can do it. This is the long way. Actually, if you use the geometric method, it's going to be the long way. There is a shorter way, which I'll show you in a minute. So here you have 6 throws, and this is if you get the 3 on the first throw, which would be less than 7 throws. So that means 1 success, no failures, obviously 1 over 6. What if you get it on the second throw? Well, that means 1 success and 1 failure. So 1 6 times 5 6 is 536. If you get it on the third throw, again, 1 success and now 2 failures. Now you say, how does this follow the geometric formula? Well, the geometric formula is P, that's the probability of success, times Q to the R minus 1. The R being the rth term on which you get the success. So since we get the success on the third term, then that means our Q is raised to the R minus 1, or 3 minus 1, which is 2 power. So our P to the Q to the R minus 1. Again, for the fourth one, P to the Q to the R minus 1, R being 4 minus 1 is now 3. This one's 5. So here's our P times Q to the 5 minus 1, which is 4, fourth power. And then for the sixth one, we have it raised to the 5th power. We multiply all that out. We do the exponents and multiply, and we get all these numbers over here. We add all that up, and you get 0.65. That's using the geometric method, basically, although I didn't necessarily write out the formula the same way, but it is the P times Q to the R minus 1. So this is the geometric method, which they are trying to introduce as new content. However, you could have avoided the geometric method and done it in a simpler way by recognizing that if you have to have a 3 somewhere before the 7th throw, fewer than 7 throws, if you have to have a success in here somewhere, then that's the same thing as not having no 3s, or not having a not 3. So the not is your 1 minus, and your not getting a 3 is your failure. So in other words, you can't fail all 6 times. If you have to have a 3 somewhere before the 7th throw, you cannot fail all 6 times, okay? So not all 5, 6, that's your failures, for 6 times, meaning 1 minus for the not, and then not being successful, failing, 5, 6 to the 6th power, because you're doing it 6 times. 1 minus that is your 0.665. So if you think about it, you can work smarter, not harder, but you got to be able to recognize that 1 minus opportunity, the not 3 for all 6. So it's a little challenging, but if you can see the work is a lot less, it can definitely save you some time. Notice this is only 2 points. You only got 3 or 4 minutes to do this. This takes some time. This you could probably do in a minute if you recognized it correctly. Moving on to question number 6, we have a group of 8 friends travel to the airport in 2 taxis. We have taxi P and taxi Q. Each taxi can take 4 passengers. The 8 friends divide themselves into 2 groups of 4, one group for taxi P and one group for taxi Q. John and Sarah are traveling in the same taxi. It doesn't say which one, just the same one. Find the number of ways in which this can be done. So notice our 8 people are first divided into 6. Doesn't matter which taxi. John and Sarah have to be together in the same taxi. Now, notice this is not about arrangements within the taxi. It's only that they're in a particular taxi. So this is combinations, not permutations. So out of these 6 that are left, we need to choose 4 to go into the other taxi, and that means the remaining 2 will go in with John and Sarah. So of these 6, because those 2 have already been established as set, so from these 6, we need to choose 4 to go into taxi P, and then the other 2 with John and Sarah will go into taxi Q. So 6 choose 4 will give that. Why do we times by 2? Well, that's because these 2 and John and Sarah could go into taxi P, and these 4 could go into taxi Q. So it can switch taxis. It doesn't say which taxi they need to be in, just the same taxi. So we need to multiply by 2. That way John and Sarah could either be in taxi P or taxi Q. 6 choose 4 is 15 times the 2 means there's 30 ways that you can do this. Moving on to part B. Now they show the taxis, but now they're looking at arrangements of seating, not just what taxi they're in. So this is moving into permutations as far as arranging of seating goes. So each taxi here can take 4 people, 1 passenger in the front, 3 passengers in the back. Mark sits in the front of taxi P. So here's taxi P, Mark is in the front. Here's 3 seats in the back. It says John and Sarah sit in the back of taxi P next to each other. So here's John and Sarah next to each other. That leaves 1 spot left in taxi P. Taxi Q has 4 spots, and they can be whoever in there. Okay. So now in this case, for taxi P, we are choosing, this is now a selection. This isn't arrangements of seating yet. This is a selection to be in the taxi with Mark and John and Sarah. So it's not about the arrangement, it's a selection. So 3 of these 8 have already been established. Mark in the front, John and Sarah next to each other in the back. So there's 5 people left. 1 of those 5 need to join taxi P. So this is a selection. So 5 choose 1 will tell us who will be in the taxi with Mark, John, and Sarah. Now, why do we multiply it by 4? This is where we get into the arrangements. So first, John and Sarah can be next to each other here, or they can be over here, up here, and this other person can be down here. This person cannot be in the middle because John and Sarah have to be next to each other. But he could be at this end or at this end. So John and Sarah can be here. That's one possibility. Or John and Sarah can be up here with this other person down in the third slot. So that's two. Then it just says John and Sarah have to be next to each other. So it could be John, Sarah, or it could be Sarah, John. Same thing with up here. If you move them up, could be John, Sarah, or Sarah, John. John, Sarah, or Sarah, John. So that's another two ways by switching John and Sarah in each of those two positions. That gives you a total of 4. So our one selected person times 4 arrangements. Mark has to be in the front. There's no change there. So that gives a total of 20 different ways for taxi P. Taxi Q is just straight permutations. There's 4 people. There's no restrictions on it. So you can either use 4P4 if you're using the permutation key, or you can just use 4 factorial. Either way, you're going to get 24. You multiply those together to find your total possible ways between the two taxis, and that's going to give you 480 ways that those 8 people can be arranged in the taxis going to the airport. Moving on, we get to question number 7. Now we get to a probability question here. Bag A contains 4 balls numbered 2, 4, 5, and 8. Bag B contains 5 balls numbered 1, 3, 6, 8, and 8. Bag C contains 7 balls numbered 2, 7, 8, 8, 8, 8, and 9. 1 ball is selected at random from each bag. Event X is exactly 2 of the selected balls have the same number. Event Y is that the ball selected from bag A has number 4. So for part A here, we need to find the probability of X. How many ways are there getting exactly 2 balls with the same number? Well, if you look at the numbers that are in common, if we start with the number 2, there's no 2 in bag B, but there is a 2 in bag C, so we can get 2 balls with a 2. So over here, what my little code is for myself is bag B does not have a 2. That's what this means. That's a code for myself. So we're doing 2s, but bag B does not have a 2. So this is the possibility that a random variable is A has a 2 and C has a 2. So if A has a 2, that is 1 out of 4 possible numbers from bag A, 1/4. B does not have a 2, so it doesn't matter what number we draw because we don't need it. It doesn't matter what number as long as it's not a 2 and it doesn't have a 2. So any one of those numbers will work, so you can just call it a 1 times 1. Now for C, we need the 2 because we're doing 2s here. So there's 7 numbers, only one of them has a 2. So for bag C, it's 1 out of 7. You multiply it, you get 1 out of 28. Now there are other numbers in common. 4 does not have a common number. 5 does not have a common number. The 8 does. If you notice the 3, no common number. 6, no common number. 7, no common number. 9, no common number. It's only the 2s that are common and the 8s that are common. But the 8s, all 3 of them have an 8. So this says exactly 2 have the same number. So we can't do all 3. We have to find the ways of only exactly 2. So it could be these 2 or these 2 or those 2. Okay? So C not 8 means A 8 and B is 8. This one is B not 8, so that means A is 8, C is 8. And this one, A is not 8, that means B is 8 and C is 8. So this is our ways of getting 2 exact same numbers, 8 and 8 from two different bags, and we exclude the third bag. So for the A8 and B8, A has 1 8 out of 4. The B has 2 8s out of 5. And then for the C, we do not want the 8. So there are 3 numbers left. 3 numbers left out of these 7 balls. So there's only 3 out of those 7 that will work. Number of desired over total possible. So 3 numbers that do not have an 8. Multiply this up, you get 370. Now for the A8 again is 1/4. Now the B is not 8. So if we take the 8s away from the B, that's 3, 3 left out of 5. 3 out of 5. And for our C8, there are 4 8s out of 7. So 4 out of 7 gives us a total of 3 out of 35 for that. Now we go on to the A not being an 8. So 3 out of the 4 are not 8s. The B has to be an 8, so that's 2 out of the 5. And the C needs to be an 8, so there's 4 possibilities out of 7. You multiply that, you get 6/35. You add all those up. Don't forget you got 4 numbers here. You get 47 over 140, or if you change it to a decimal, 0.336. Notice it's 5 points. You've got 7 minutes to do this. You have time, but you do need to think that this is exactly 2. So that means with the 2s, it wasn't a problem because only 2 of the bags had a 2. But for the 8s, you're going to have to make sure you get only 2 and not the other one. Okay? So on the not, you're looking at the non-8s. So you have to be a little careful with that, but you can do it. Then find down here, I found P of Y because of the next question down here. The P of Y is the event that Y, that the ball selected from A is a 4. Well, A only has 4 balls, and there's only one of those that's a 4. So the P of Y, or the probability that the ball selected from bag A is 4, is 1/4. It doesn't matter what B and C are, so they're just 1s. And you get a 1/4 for the event of Y happening. So again, B and C doesn't matter. You're just looking from the 4 from bag A. So the reason why I did that is because we're down here. We have to find the intersection of X and Y. Same thing as probability of X and Y. This is Venn diagram notation for intersection. Means both of those have to be on the same pathway. Determine whether or not the events are independent. So the probability that A is a 4, meaning it can't be the 2, and the probability that the other 2 numbers are the same. See, this is X and Y. So the Y part is that A is a 4, and the X part is that 2 numbers are the same. So if A is a 4, that's 1/4. That automatically disqualifies that both marbles can be, or both balls can be a 2, because one of the 2s is in bag A and A has to be a 4. So that means these need to be 8s. So the 8s are 2 8s from bag B and 4 8s from bag C. So you have a 2 out of 5 for B being an 8 and 4 out of 7 for C being an 8, and the 1/4 for A being a 4 to satisfy the Y. So both these have to be satisfied. That gives us 2/35. This is the intersection, 2/35. To show whether or not they're independent, we have to show that the intersection is the multiplication of the X event times the probability of the Y event. So this was the answer that we got for the intersection, 2/35. Our probability of X was up here with 47 1/40. Our probability of Y was 1/4. And if we multiply 47 1/40 times 1/4, we get 47 over 560. That is obviously not equal to the 2/35. Therefore, these are not independent. So make sure when you're showing whether it's dependent or independent, make sure you've done P of X separately, P of Y separately, your intersection separately, then multiply your PX times PY and check that against your intersection of the two. If they're equal, they are independent. If they are not equal, it means they are not independent. The two are related somehow. Moving on here to the end, I believe this is our last question, says, find the probability that two balls are numbered 2 given that exactly 2 of the selected balls have the same number. So this is conditional probability because of this given statement. So the probability that there are 2 balls numbered 2 given that there are exactly 2 balls with the same value. So your formula is the probability of the intersection of the 2 with the exactly 2 being the same over the probability that there's exactly 2. So again, the probability that the 2 balls are numbered 2 was back up here. The probability that our 2 balls are numbered 2, which also happens to satisfy that the 2 numbers are the same, so it is the intersection, is 128. So both balls are 2, and it satisfies that second part that the 2 are the same value. So the 128th is the top one here, and then the probability of them being exactly 2 of the same number is what we found here as the total, the 47 1/40. That was all the possible ways of getting exactly the same number, 2 exactly the same 47 over 1/40. So that is the bottom number. You divide those, you get 5 over 47, which is 0.106 if you're to write it in 3 significant figures, or it might even be exact. But here's your answer to the conditional probability question. That then is the end of the test. We've worked through the entire specimen paper. All the different question types are shown, and we went through, and I tried to remind you of things that we learned in the video series for statistics. So I hope that helps you. Again, pay attention to your time. You need to be able to do it in 1 hour and 15 minutes. Half of it is structuring your thinking so that when you see the question types, you know your thought process on how to work through the question so that you're not wasting too much time thinking about it. You got to be able to look at it, identify it, follow your procedure, get that answer down. 1 hour and 15 minutes, you got roughly 7 or 8 questions that will be asked. That concludes our statistics trial test here for the specimen paper so that you know what to expect for the Cambridge examination. And again, as always, thank you for joining me. Thank you for watching the statistics series. Hope that's helpful to you, and I hope that you can be successful in these Cambridge examinations. And as always, good luck, and see you again next time.